Let me start with Marianne Noelte. So she's a professor in mathematics education with a focus on primary school at the University of Hamburg. But maybe even more important, she's the head of the MCG, so the International Group of Creativity and Giftedness, but also she's the head of the William Stern Society or William Stern Gesellschaft, a local enrichment group in Hamburg. And furthermore, as a, I should say, maybe daughter program would be the direct translation. No, the William Stern Society does not focus on primary school children, but there's a further program called Prima, so pre like primary, and this focuses on primary school children in the very same spirit of enrichment. Yes, maybe these words for Marianne Noelte, and then let me introduce Torsten Fritzlar. He's a professor of mathematics education, again, with a focus on primary school, but also on the use of media for primary schools at the University of Halle-Wittenberg. He also has a focus on problem solving, so we did not pick people here at random, of course. And maybe as mentioned yesterday, he is a reviewer for the Mathematics Olympiad for primary schools children, and also highly involved in the Society of Didactics of Mathematics in Germany. So I try to stick it to about 5 minutes. I'm sorry if I leave you with too much time, but now, yeah, it's a pleasure to open your panel, so I'm really looking forward to it. Thank you.
First, we thought that we could give you some theoretical background of problems and how we foster in the a sense of the Hamburger model, and now we changed the program. I will start with the question how to identify mathematically gifted students in times of Corona pandemic, and in the second part, after about an hour, we will change and Torsten Fritzlar will start. We hope that we have a lot of time for discussion in the meantime, and we hope that many of you will participate. In Hamburg, we foster mathematically gifted students since at the primary grade level since more than 20 years. We started since because of the children asked us to start to continue the fostering process also at the secondary level. And we are very happy that since 2019, the authorities of Hamburg told us that they will pay the fostering program up to the 10th grade. Our aim is to educate the students in a way that they learn to behave like little mathematicians. So we offer them challenging problems. The problems allow investigations, doing research while learning how to do research, and the problems are complex are challenging due to their complexity. What is meant with complexity? We think they are complex because of the amount of information the children have to deal with. They have rich mathematical contents. The problems are obviously open, but, and this is very important for the primary grade students, it is no more than the usual knowledge of the respective grade necessary. We are persuaded that it is possible to develop mathematical thinking processes even at primary grade level. So although the students are not capable of using the symbolic mathematical language, they learn to reason mathematically. When we identify the mathematical gifted students, we use the same kind of problems which we use to foster these students. I avoid a discussion about the characteristics of mathematics here because I think when I give you some examples, you see what I'm thinking about. Our fostering program is based on the ideas of Professor Kieswetter. He defined at the beginning of the 1880s patterns of action. One of this, which are advantages in problem-solving processes. He observed many students, he observed also mathematicians while they did problem-solving, and he saw that there are several patterns of action. Later, he called them higher order, not higher order thinking skills. I will go back to it later, but they are the same. One is switching between levels of representation. For example, an algebraic representation of a problem and a geometrical representation offers the possibility to see solutions, finding connected problems. That's what we today say to posing problems. Organizing material in order to recognize eventually different patterns. That can start even at the first grade when students find a kind of orientation in the many information they got in a working process. Developing and testing of hypotheses. This is a process which is, this is a pattern which is very difficult for the students at primary grade level because in schools, normally they are not used to. Reduction of complexities through meta-symbolization, building superscience, and this is called chunking by psychologists, recursion, and intuitive use of strategies already indicated or further heuristic strategies. As I told before, with these kinds of problems, we test students and we foster students, but usually our talent search process starts with trial lessons. This is very important because the level of mathematical education at primary grade level is very different for students. Teachers are different educated in mathematics, and the classes have a different level, and so it is important to, in a way, equalize. We cannot equalize all these questions which are risen with this problem, but to show the children what they can do when it comes to mathematics. Every child gets one weekend. On Friday, they work on one problem, about 90 minutes, and this shows you that these problems are different from the problems they are used in school to. They are used to in school. Our aim on Friday is self-evaluation. Do I like this, these kinds of problems? And we always ask the parents not to pressure their children to come again to the university if the children show that they really are not interested in our kinds of problems. On Saturday, we prepare them for the math test because also as well as the complexity of problems, they are not used to, students at this age are not used to tests. They have perhaps written tests about timetables, but this is not comparable to a test about problem solving. So we show them how to write down explanations. And then we have a third and a fourth Saturday. On the third, on the second and the third Saturday. On the second Saturday, the children write the math test, and on the third, they are tested with a language fair intelligence test. Now, in the pandemic times, we have the situation that the students are not allowed to come to the university. So we cannot offer trial lessons in presence. And we cannot test the students under the usual conditions. What are we doing now? step is, instead of trial lessons, all students who applied for participating got a problem. We were very glad that not as much students as normally applied for participating. Normally we get up to 500 students who are interested in the Prima program. But in November, we only had 175 students who applied. And we wrote an individualized feedback for every child. And my colleague and me, we went to every feedback every child got, so that we are very proud about the people who work with us, for example, like Karl Heuer and Dennis Sarikaya, because of the way they wrote the feedbacks to the children. In addition, we explained the solutions in a video. This is the example of the first problem we posed to the children. It's only part of the problem. The structure of this triangles is based on the Pascal triangle, of part of the Pascal triangle. If you add the 0 and the 1, you get 1. If you add the 1 and the 2, you get 3, and so on. The same here, 12 plus 1 equals 13, 1 plus 12 equals 13, 13 plus 13 equals 26. And we asked the students how, for example, how many solutions are there for the final number 5? And another question, another of the different questions we asked them is, which numbers can you produce beside 3, 5, 26, and 29? What can we see? Going back to the patterns of action of Kieswetter, we saw that some of the students organized their material. For example, these are the solutions for the number 5, and you see if the children wrote them down in such a way, we can be sure that they saw the symmetry between the two results. So we see that they can work systematically. And we also saw whether they are capable of developing hypotheses. Some of them explained, for example, that they can find every number using the 0 in the first row, 0, 0, and any number. Some of the students wrote down a variable. I do not know whether they are really familiar with the context of a variable, but also if they wrote down 005, 006, 007, and so on, we know that they got the main idea. And we also saw something which we can describe as building super science. We also saw recursion about the intuitive use of strategy already indicated, or further heuristic strategies. We do not know so much. We couldn't see so many. We couldn't get so many information from the students. Recursion, for example, when it comes to the question whether what kind of numbers they can find, you see here, for example, the number 5, and you can see that there are different possibilities to. Now I do not know the word for zerlegen. To find different sums for the number 5. And this is the way to start with the result and not with the first row. The second step is a second problem. We were no longer capable of writing an individualized feedback because it took so long time, but we developed a presentation with possible solutions. And one of the students wrote us a solution in English. I was very glad about this. But first, I want to introduce the second problem. With this problem, we want to test a kind of creativity, of motivation and endurance. The following figure can be made from squares. How many squares does this figure consist of? How did you find this? Explain your way. And most important, describe at least 3 more ways to find the number of squares. I asked this question also in regular lessons, and the most common way to find the number of squares is to count the squares, but you can also count squares while you see several patterns. And this is the result of Eduard. When I turn the page 45 degrees left or right, then I see it's like a square. I see there are on the borders, which I colored blue, are 5. When I saw that, I was thinking it was like 5 times 5 equals 25, and with the red was 4 times 4 equals 16. After that, I calculated 25 plus 16 equals 41, and I knew that was the result. This is the kind of result, I think, which is very nice. I normally find this not so often in regular classrooms, but often with students who have certain capability in mathematics. Here are the other solutions which Eduard sent us. And you see that he also described what he was doing. The explanation for children is sometimes write down what you calculate or write down what you think. This is a solution you find very often in regular lessons. We asked the students what is the best way to solve it. The boy answered the possibility in the 1.1 is the best because it is easier to multiply the squares of 2 different colors and then add them together. And we asked the students also, how would a mathematician solve the question? He answered they would do the same. Here are the results of another boy. He decided that the first way is the same of Eduard. It's the best way to calculate it, but you see that these boys also see different patterns. Here, I think this is very interesting. You see 1 plus 3 plus 3 plus 1, and this 4 times, and then he calculated the 9 little squares which are left. We asked them, how would a mathematician solve the question? And you see that he used a different idea. He integrated the figure in a square. This is also a solution which parents, if we give them this problem, like. And all about, we see that both boys solved the problem. We can see that they are highly motivated because they did more than what we asked them. And they changed the perspective on the problem, like in the first solution. This is connected with the patterns of action of Kieswetter, with switching between representations and with seeing patterns. He changed the boys changed the representation they got in the first row, and they always changed the representation with the different patterns. This is a kind of pseudoscience, what we see with the last boy. And altogether we got about 19 different possibilities. I do not know whether they, in the meantime, they found more, but I think it's, I'm very content with this result. As I said before, the students get a presentation with several possible solutions. Now we are preparing this presentation and we evaluate their results taking into account the correctness and the quality of their solution. We want the correctness is easy, whether they calculated or counted it in correctly or not, and the quality is combined with the question whether they explained their solution. For example, such a picture is interesting, but and I think we get many ideas if we see this picture, but it's also very, very interesting to see that the first boy explained what he had done. And this is a kind of quality which I think which is very high, especially for an 8 or 9-year-old boy. In the step 3, we test the students, and we had to composite the groups. We will send, we haven't done this so far, we will send the students 2 problems to work on at home, and we select the best students to participate in a preliminary group. Normally we build the groups, we build fixed groups, but because we do not know whether the parents will help the students or not during the tests, we will ask more students than normally to participate. And after 2 or 3 sessions, we will make the final decision about participating. We have some questions in this context. For example, what is with students whose parents are not that as well educated as other parents? We have children from mathematicians, we have children from engineers, we have children from families which have really, we wouldn't describe them as well educated. And the next question is, we cannot support them during the problem-solving process. What impact has this on our evaluation? And the next problem is that we cannot hinder parents to support their children while they work on the test, as well while they work on the problems. One of the children is the son of a mathematician, of a colleague of us. We didn't talk with him. Yes. Nevertheless, we got the impression that the individualized feedback was very helpful, and that with the second task, we see more students who try to write down their ideas. And this is my part, and I would like to get some, to open the discussion. What do you think of this kind of talent search process? And perhaps you have other ideas what we can do or you have developed other ideas how to select students for such a program, especially such a high number of students during these times of Corona.
Okay, so I'm very happy that you can see the slides, I think. Yes, the topic of our panel is how to work with gifted students in times of Corona. And as you know, we had planned 2 parts, and the part of Marianne was how can we identify mathematically gifted students in times of Corona pandemic. And now I want to say something about how can we foster mathematically gifted students in times of Corona pandemic. But I hope we will have a truly interactive panel. I want to give only a short talk and then we can have an intensive discussion, I think. So how to foster mathematically gifted students in times of Corona? So I want to say something about the theoretical background of fostering mathematically gifted students, like common implementations in relevant projects at some German universities, and then possibilities in times of Corona. But I think there will come many variety of questions and challenges with Corona. So if one wants to foster mathematically gifted students in a sustainable way, he or she has to make many decisions. There are decisions on the identification process or the procedure, on the aims of fostering, decisions on the content, the methodical arrangements, tutors, organization, and so on, but also on how to evaluate fostering efforts. And of course, these decisions are influenced by held conceptions of mathematics, giftedness, but also influenced by conceptions of teaching and learning. And of course, these conceptions are not dependent from each other. And of course, there are also political, social, economical, ecological conditions that frame the whole project. And these can also have a limiting influence, currently the coronavirus. So, of course, I cannot talk about all these elements, but I want to say some words about the concept of giftedness and conclusions for fostering projects or programs. Marianne told already something about concepts of giftedness. Once again, only some words about the Hamburg model concerning mathematically gifted students. Of course, there are a greater number of approaches to describe mathematical giftedness, but I think the model by Kiesewetter, which is already almost 40 years old, had a great influence in the German language mathematics didactics. So I think it could be very interesting to know it and to discuss about it. Kiesewetter founded a project for fostering students in the 1980s, and he constructed a catalog of categories of mathematical thinkings or patterns of actions, which is useful in working on mathematical problems. But it's important that they can give hints for high mathematical potential only if they are used in mathematically rich situations. And you can see these patterns of actions: organizing material, recognizing patterns or rules, recognizing problems, constructing related problems. There's a problem posing aspect, changing the representation of a problem, recognizing patterns and rules in this new area, comprehending very complex structures and working within these structures, and reversing processes. This description refers primarily to older pupils in the secondary grade. Of course, there are also approaches to describe mathematical giftedness at primary school age. For example, at least in Germany, pioneering work of Friedhelm Kepnick, published in 1998. And some years ago, Daniela Asmus finished her dissertation that examines the cognitive characteristics of mathematical giftedness in primary grades. Not only profoundly theoretically, but she also empirically investigated these abilities for second grade students in a very detailed way. And this is an important result of her dissertation, illustrating the structure of cognitive characteristics of mathematical giftedness. And of particular importance is the ability to think flexibly, the ability to construct and use mathematical structures. Sorry, this is you can see on the part above. And the other abilities, like to reverse lines of thought or mathematical creativity and so on, are based on this very important ability to construct and to use mathematical structures. And following these conceptions, especially Kieswetter's conception of patterns of mathematical actions, to foster mathematically gifted students means to enable them doing mathematics. And doing mathematics is problem solving and problem posing embedded in theory building processes. I think that is a very important idea developed by Kieswetter, which could be very fruitful for the long-term fostering of mathematically gifted students. And such a theory building process normally begins with an exploration of a mathematically rich situation from which a first question is gained. Occasionally, a problem is also already given, especially for younger students. From dealing with it, with a problem, from varying and expanding the questions, and out of achieved results and methods, developed aids and strategies, from the creation of a system of concepts and logical linkings, a netting of theory emerged, which must be finally optimized and preserved. And this described model of theory building processes is only a provisional and approximate one. For instance, social aspects concerning the work in research teams are not included, but I think it provides a theoretical basis for developing appropriate working environment materials to foster mathematically gifted students. And for younger or mathematically less experienced pupils, a gradual introduction into this theory building processes is necessary. So usually one starts with suitable problems or problem fields, but in my opinion, it's important to keep in mind the possibly long-term goal of theory building processes in elementary mathematics. So comes the question, what are special requirements for suitable problems for younger students? Marianne said something about this, so I can, I think I can go to the next slide. These are the suitable problems or possible characteristics of suitable problems, which are also called progressive research problems, progressive Forscheraufgaben, a concept developed by Marianne Nolte and colleagues. So how is the fostering of gifted students implemented in university projects under normal conditions? As Marianne said, there is a strict, more or less strict selection of pupils by specific mathematics-related tests, possibly supplemented by observation at first meetings and intelligence tests. And the regular fostering meetings are conducted at university and realized by relevant, interested mathematics didactics researchers. And frequently, student teachers also participate in these projects. They had to conduct these sessions. They observe or analyze the meetings, especially processes of problem solving, problem posing, communicating, collaborating, and so on. And at the university in Halle, where I come from, we have also such a project, the Math Investigators for primary students. And our aim is that the pupils work independently in mathematics, gain heuristic experiences, apply and deepen knowledge and skills. They should work creatively, develop appropriate ideas about mathematics, enjoy mathematics, of course. They should communicate and cooperate. We try to combine fostering teacher education and research. And concerning the teacher education, our aim is to sensitize the teachers or the teacher students to the thinking of mathematically gifted children, their abilities, their needs, and possible challenges in everyday school life. And the students should gain practical experiences regarding the fostering of pupils and the development of suitable working materials. And for us as researchers, the development and evaluation of working materials is interesting or important. And we also are interested in students' mathematical abilities, mathematics-related conceptions, problem solving, creativity, and so on. So I think in regular times, under normal conditions, we have very interesting and very powerful teaching and learning labs. But now we are in the times of Corona pandemic. So how can we keep in touch with mathematically interested or gifted students? And how can we keep students interested in doing mathematics? How can we enable students to work on mathematically rich problem fields together with others? These are important questions and difficult questions, I think. Now, we try to conduct digital math investigators. We have small group meetings via web video conference systems. For instance, 4 pupils, primary pupils, and 2 teacher students work together in small groups. Before the digital meeting, pupils receive worksheets to work on, and the pupils send their solutions back to the teacher students 2 days ahead of the session. And in the meeting, tutors take up pupils' ideas in a first discussion. The approaches of the students are discussed, justified, compared, extended, transferred to more difficult problems, generalized, and so on. Further related problems are worked on. But there are many challenges of digital math investigators, I think. Challenges for us as researchers concerning the construction of suitable problems or problem fields, organizing the groups, meetings, etc., supporting the teacher students. Challenges for the teacher students concerning the designing worksheets for independent work of the pupils on entrance problems, and concerning the elaboration of possibilities for the digital work on problems. And there are challenges for pupils. They have to independently understand entrance problems. They have to tackle the entrance problems on their own. And I think it's also very difficult for young students, for young pupils to communicate and collaborate via video conference. So these are some questions Marianne and I could not answer we would put it to discussion. How to keep in touch with mathematically interested or gifted students in times of Corona pandemic? How to keep students interested in doing mathematics? How can as many conceptual ideas as possible, like theory building processes and elementary mathematics, be transferred or saved to the digital world? And what do you think? Are there special requirements for problems or problem fields or progressive research problems or problem posing used in digital meetings? And how can we foster students' development not only in mathematics but also in communicating and collaborating with the mathematics? And how can we handle the often unnecessary support by parents, or the often detrimental support by parents? That's my short introduction into an intensive discussion, I hope. Thank you very much for this time.
When we see the children in presence, we get many more information about them than what we see when they are on a computer screen. And some of my research subject is twice exceptional children. And with these children in regular situation, when I see them in presence, I get an impression about ADHD, about difficulties in language, about difficulties in behavior, in listening, and so on. And these are all information we cannot get in the. We cannot observe the children. We cannot observe their natural behavior, so it is difficult to understand them. And another aspect, some of the students who are gifted, some characteristics of students are also a hindrance in their development, because when they want them to be the best and ask themselves to be the best in all their behavior and in all their productions, the performance, when we meet them in regular lessons, we can support them also in their Anspruch, in their need to perform as the best. And this is again something we cannot do in times of meeting them only on a computer screen. Beside this, I would give the problem of talking about this discussion to Torsten, because you mentioned so many ideas and you gave so many hints what we can do with the students that it is difficult to come to a summary. So perhaps, Torsten, you want to add something?
Well, thank you. No, I cannot add so much, but I would to say thank you very much for the many ideas and good ideas, because it's very important in my eyes to, as you said, to keep the children engaged in mathematics, to keep them interested, because also gifted students need suitable offers or need fostering. They will not develop their gift on their own. And so we have to come in touch with the students. We have to make offers, but in times of Corona, it's difficult. It's especially difficult for young students. It's especially difficult for students with in poor families. And so I think these are very important questions we have to discuss. And so I want to say thank you very much for the ideas, and I think we should continue our discussions and our work, of course, also our work. Thank you very much.
Thank you also from me. Thank you very much. And think about the parents who are working at home in a home office with many children in different ages. A small room, a small desk where you have to work. We have really hard times, and thank you for all the good ideas you had.